Hello, this will be the last video for Chapter 7, the last of the 4 reactions of alkynes called hydrogenation. You can guess from the name, and in fact you already know what hydrogenation means. It just means we're going to be adding 2 hydrogens across the triple bond. Essentially the same reaction as reaction of alkenes, in which we added 2 hydrogens across the double bond. It's also going to be syn addition, and the only difference is with an alkyne, of course, you add a pair of hydrogens and then maybe perhaps another pair of hydrogens to go from a triple to a double to a single bond. Please read section 7.8. It's on pages 270 to 271. Alkynes can add 1 or possibly 2 equivalents of hydrogen. So here are the reactions that we're going to learn in this chapter. First of all, you can just add hydrogen with a typical catalyst, the same kinds of catalysts we used for alkenes: nickel, palladium, platinum, lots of other examples. And you're going to add 1 pair of hydrogens across the triple bond, and it's going to become a double bond. But this is the one reaction among those of alkynes that we've learned about where the scenario is that you can't stop it in the middle. As soon as 2 hydrogens add to the triple bond, it becomes more reactive. So the alkene reacts faster than the alkyne does, and so you can't really stop it after adding just 1, even if you only put 1 equivalent in. And so really this reaction is only useful if you want to add 2 pairs of hydrogens. So you might as well go ahead and put in excess and go from an alkyne directly to an alkane type single bond. But when you present a challenge to a chemist, like you can't stop an alkyne at the alkene point, they will meet the challenge. And so some smart guy named Lindler came up with a catalyst that involves palladium on calcium sulfate with some other stuff thrown in. In any case, it's called Lindler's catalyst, and that's all you really need to know. Just name it Lindler's catalyst. So when you add 1 equivalent of hydrogen and Lindler's catalyst, it just adds 1 pair of hydrogens across the triple bond, and it becomes a double bond. Notice it adds stereospecifically syn, which is very useful because that allows you to make alkenes with a syn stereochemistry, and that's one of the few ways that we have of doing that, because typically when you make alkenes, it tends to want to be trans, and so in order to make a cis double bond, this is a very good way to do it. Start with an alkyne and turn it into a cis alkene using hydrogen and Lindler's catalyst. But then the question arose, is there any way stereospecifically of making a trans double bond and stopping it after this addition of 1 hydrogen? And the answer is yes. But it turns out it's not a hydrogenation. At least technically you're not adding H2, whereas in the other 2 you're adding hydrogen gas. In this case you're not. You're adding sodium metal in liquid ammonia. Very odd combination of things. First of all, what is liquid ammonia? Well, ammonia is a gas, but if you cool it down enough, like with almost any gas, you can turn it into a liquid. So this is done under very, very, very cold conditions, cold enough that ammonia is actually the solvent in this case. And then you take your alkyne, you dissolve it in the liquid ammonia at very low temperatures, and you then add little pieces of sodium metal. This is not sodium hydroxide or sodium hydride or any sodium compound. This is literally sodium metal. Putting in chunks of sodium into the reaction mixture. Initially it turns blue, which is very interesting, but then very quickly turns back to colorless again, and what you find out is that you've added 2 hydrogens across the triple bond, but they add anti, and so therefore you end up with a trans double bond. So there are the 3 hydrogenation reactions that you need to know for alkynes. Here are some examples. So let's start with this. Alkyne happens to have a cyclobutyl group on the end, and it's a terminal alkyne, meaning hydrogen on the end. If we put in excess hydrogen with nickel catalyst, what are you going to get? Well, you're going to add 2 hydrogens here, and that becomes CH3. You can add 2 hydrogens there, and it becomes CH2. The triple bond becomes a single bond, and this acetylenyl group becomes just an ethyl group. What if we started with an internal alkyne? In other words, it's not a terminal alkyne, but we do the hydrogen with Lindler's catalyst reaction, and it turns out then, of course, that you get the cis addition, and you end up with this fairly strained cis alkene, but that's what you get because the reaction is specifically syn addition. Doesn't go on further. And finally, if we started with 2-pentyne and added sodium and liquid ammonia, you would end up getting trans 2-pentene. Again, fairly simple reactions. Now here's some examples for you to do. Let's look at this particular molecule, which I've drawn in a stick figure type thing, and remember that if you draw a triple bond in a stick figure with these angles to represent the carbons, that's really not the shape of the molecule, it's actually linear. But sometimes it's easier to see the structure if you draw an angle there so that we remember this hydrogen and nickel. What does that do? Turns the triple bond into a single bond. Of course, there's 2 more hydrogens here and 2 more hydrogens here than there were to begin with. But again, with stick figures, you can't really see those hydrogens, but we know they're there. What if we took the triple bond molecule with hydrogen? Oh, by the way, this is 4-methyl 2-hexyne. So let's take 4-methyl 2-hexyne again, and this time react it with hydrogen and Lindlar's catalyst. And what do we get? Well, we're going to add 2 hydrogens across the triple bond. It's going to become a double bond, but it's going to add cis or syn addition, and so the 2 hydrogens have to end up on the same side, and so the 2 carbon groups have to end up on the same side, and so we get the cis molecule. And so I've drawn this double bond in a way that makes it look like it's cis. And then this molecule, we start with the same alkyne. This time we're adding sodium and liquid ammonia. Again, it's going to add a hydrogen here and a hydrogen here, but they're going to add anti, and so we get the trans molecule. And so again, this is just trans 4-methyl 2-hexene. And that's the end of the lecture. Thank you for your attention.